In this video, we will pick up the concept of pressure. We will begin studying fluids. In fluids, we're going to particularly study static fluids, thus fluids for which the sum of the forces are zero. In a fluid, we have what is called a distributed force problem. And that means that we're not dealing with a single force like we had been in the past on a block here, but instead forces exist everywhere. For instance, they'll exist on the sides here, and they'll exist in the bottom here, and to the side. And so, rather than trying to draw an infinite number of arrows or anything, the number and the amount of the force will in fact depend upon the size of the object. A fluid is an object that can change its shape based on the vessel that it's put into, and it also has no shear capability. What I mean by that? I mean that if you put a force in horizontal to the surface, then the fluid will move. It'll accelerate. So the only way to have it is not accelerate is that the force has to be either compressive in the sense that it has to push down perpendicular to the surface. This is very different than what we've dealt with a solid. But the concepts of Newton's law are not different. So what we need to do is to redefine the way we talk about forces in terms of a new concept called the pressure. So here's what we're going to do. We still want to talk about forces, but since the forces are distributed over an area, for instance, we're going to talk about force per area. And since the force always comes in perpendicular, because if it comes in sideways, it would push the fluid to the side, which should not be static, we'll only talk about the force perpendicular to the surface. So the definition of pressure. Pressure, by definition, is the force divided by the area. And this force is a force perpendicular. Now, in theory, we could have the force changing as we went from different places, and so we really should think probably about an infinitesimally small surface. But for this class, we're not going to make a distinction because the problems we're going to deal with are not calculus-based problems. We're just going to say it's the force divided by the area. So if you had, for instance, a 2 meter by 2 meter surface here, and if I applied a force of 2 newtons, then the pressure would be 2 newtons divided by 2 meters times 2 meters, which would be 0.5 newton per meter squared. Now it turns out we've actually got a name for a newton meter squared. It's called a Pascal, after Dr. Pascal, who did a lot of work in this field of fluids. Anyway, this is the definition of pressure. The force perpendicular to the surface divided by the area of that surface. As I mentioned, an ideal fluid can't resist shear forces. And so we know that the force will be perpendicular. Forces are vectors, yet we're not acting like pressure is a vector. We're just taking the magnitude and dividing by the area. The reason for this is much like dealing with one-dimensional problems. Because the force has to be perpendicular to the surface, so it's either pushing in or pulling out, there's no need for the full range of vectors. We can treat it like a scalar and just note the direction of the arrow. So, yes, pressure has a direction. It makes a difference whether the air pressure in the tire is pushing outward on the tire or inward. It must be outward, otherwise the tire would collapse. But we can treat it as just a plus or minus, and therefore treat pressure like a scalar. And that's what we're going to do. The units, as I mentioned, are Newton meter squared, and we define those to be a Pascal, which we just simply use a P capital because it's the name of a person followed by a little a. Now, a lot of times you're going to have atmospheric pressure in problems. And so we're going to need to be able to put the atmosphere in terms of Pascal. It turns out that the atmosphere is quite a few Pascal. It's 1.013 times 10 to the 5th pascals. It's also equivalent to 1.03 0.0013 bar. This is because 1 bar is 1 times 10 to the 5th, 100,000 pascals. Another useful thing is that you talk about things in terms of torr. This has to do with thermometer or barometers. 760 torr is equal to 1 atmosphere. And last but not least, 14.7 pounds per inch squared. This is called a PSI. So there are many different unit systems that are used. This is an English system, and it's useful when dealing with things here in America. This is often useful when dealing with barometers and such, and you'll see people who use torr in vacuum systems in science. The bar is just advantageous to get rid of this 10 to the 5th. And you can see the atmosphere is about 1, so it's about 100,000 pascals. All right, but this is the pressure in the atmosphere at standard temperature. Now, what about the difference between pressure and force? A lot of times you'll see some interesting things. Pressure brings some cool things to talk about. For instance, people will lay on a bed of nails, and the nails are very sharp, and you would think that they would get hurt, but yet they're not hurt. Other types of magic, you'll see a person walk across all sorts of crushed glass barefooted, and they don't get cut and don't get hurt. And the reason for that is that a lot of times when dealing with strength of materials and other things, it's pressure that's important. It's not just the force, but how the force is applied and over what surface area. So all of these deal with the fact that pressure, not force, is usually what causes an object like your skin to break. If an elephant was to step on your foot, they'd crush your foot. But they wouldn't penetrate your foot. They'd just smush it. But a girl's high heel shoe, stepping down, and you can put a lot less force, but it's over such a small area, the pressure is much greater and it will penetrate the skin. This is the reason we make nails that are sharp. This is the reason we make hypodermic needles that are sharp. If you make them sharp, greater pressure, and pressure is what punctures the skin. So let's look at this kind of from an old game that people used to play. They would line people up, grabbing hands, and people on another team would try to run through those arms and break through. And if they broke through, they got to capture the person. They called it Rover Red Rover. In the same way, when you push down on a bunch of atoms, the atoms are kind of held together. If the pushing down is spread out over a large area, then it can't come in and drive any one of the atoms apart, and the skin stays connected. But if you put all of the force in a very small area, just like running a bunch of kids, not one kid at each person, but the whole mob, smacking right on one of them, you'll break through and penetrate this line. Militaries figured that out years ago. Try to bring superior forces to a single point in the battlefield. So high pressure with the same force can penetrate. So it's not the force, it's the force over area that's often important in material science, and it's certainly what's important in fluids. Let me show you talk about one more example. Think you're floating, and there's water. If you ball up for a variety of reasons and jump on the water, then the water will penetrate and you'll be able to cut right through it, right? This is why a diver, for instance, goes in like this into the water and they're able to splash. What you don't want to do if you're diving, for instance, is dive horizontally and come down. Why? Well, here you have great pressure and you penetrate. Here you may have the same weight, but you do not have the same area, and so you cannot penetrate the surface of the water. Of course, if you're wanting to float, this is what you want to do. You don't want to penetrate the surface. You want to stay on top of the surface and use surface tension to help keep you up. So, main things, just a very simple formula. Pressure equals force over area. And a few conversions. It's all in this section. Learn the conversions, know the units, make sure you know what pressure divided by area is. We're going to use it a lot, this connection between force and pressure.